Good morning, class. We are looking at Chapter 4 review, a portion that pertains to the fourth exam. A big chunk of it was covered in the previous exam. So let's go to new stuff. All of this covered in the previous exam. The mean value theorem, the Rolle's theorem. How derivative affect the shape of a graph, and of course, graphing. We want to go to the new stuff. Indeterminate forms and L'Hopital's rule. We want to find the limit using the L'Hopital's rule. The L'Hopital's rule tell us if we plug in and we end up with 0 over 0, or infinity over infinity, that's the time we can use L'Hopital's rule, in which case we take the derivative of the top over the derivative of the bottom. As you look at this first example, you plug in 1, you get ln 1, which is 0, over 1 minus 1, which is 0. So for you to use L'Hopital's rule, your first step is to show that it is equal to 0 over 0 or infinity over infinity. Otherwise, you cannot. So you have to write. Your first step is this. You have to write this and then move. Now we take the derivative of the top over the derivative of the bottom, which is 1 over x over 1, and replace the x. We will get the answer 1. For the next example, if we replace the x with 0 in the numerator, we get e to the power of 0 minus e to the power of 0 minus 2 times 0, which ends up being 1 minus 1 minus 0, or 0. The denominator, x is 0, sine of 0 is 0. So you do have 0 over 0. Therefore, we can use L'Hopital's rule. We take the derivative of the top, e to the power of x plus e to the power minus x minus 2 over the derivative of the bottom, which is 1 minus cosine x. We plug in x equals 0, and notice the top is e to the power of 0 plus e to the power of 0, which is 2 minus 2 equals 0, and the bottom is 1 minus cosine of 0. Cosine of 0 is 1, so 1 minus 1 makes it 0. Again, we are dealing with 0 over 0. L'Hopital's rule is used again. Differentiate the top, differentiate the bottom. And you notice the same thing, 0 over 0. So we are using L'Hopital's rule multiple times, and that's fine. Let's differentiate it again. And now when we plug in, the numerator is e to the power of 0 plus e to the power of 0, which is 2, over cosine of 0, which is 1, and the answer is 2 over 1, which makes it simply 2. And that works. I chose this question on purpose because you have to repeatedly use L'Hopital's rule. But in order for you to do so, first you have to show it is 0 over 0 or infinity over infinity. When we have a form of 0 times infinity, we can use L'Hopital's rule in the following manner. We put one of them in the denominator and we write the reciprocal of that. It becomes either 0 over 0 or infinity over infinity. So as you see the first one, x is approaching 0 from the right, so that's 0. And ln of 0 from the right is negative infinity. I hope everybody remembers the graph. And therefore, we are looking at 0 times negative infinity. And so we are going to rewrite this in the following manner. We take either x down, we make it 1 over x, or ln x down, and we make it 1 over ln x. However, in this process, you have to be wise, choose it such that when you want to differentiate, it's really not that difficult. If you take ln x down, it's more difficult. But now if you plug in, you get negative infinity over infinity. Therefore, L'Hopital's rule can be used. We take the derivative of the top, which is 1 over x, over the derivative of the bottom, which is, by now we know it's negative 1 over x squared. Needless to say, if need be, class, you change 1 over x, you change 1 over x to x to the power of -1, and you do the math using the power rule. But I guess by now we, at the very least, are familiar with this. This expression, which is a complex fraction, simplifies to negative x, and the limit of that is therefore 0. The next example, if you let x go to infinity, square root of x goes to infinity, and e to the power of negative infinity over 2 is 0, so the product of infinity times 0. I hope everybody understands what we just plug in, and notice that e to the power of negative infinity over 2, which is negative infinity, makes it 1 over e to the power of infinity, which makes it 0. So we take one of them down, and I hope you realize, because e has a negative exponent, it's easy to take it down and make it positive exponent. Plug in and you get infinity over infinity. Therefore, we can use L'Hopital's rule. All right. Square root of x is x to the power of 1/2. And you know how to differentiate that. Let's just quickly show that. You can differentiate this by writing 1/2, x to the power of 1/2 minus 1, or negative 1/2, which becomes 1 over 2 square root of x. E to the power of x over 2, maybe just to be on the safe side, we write this as e to the power of 1/2 x. So we notice the exponent is half of x. That means the coefficient of x is 1/2. Okay, and therefore it makes it easy to differentiate it accordingly. The derivative of that is e to the power of 1/2 x times 1/2. So I hope everybody's clear on that. Now, again, we have a complex fraction. We rewrite it as such. We replace the x with infinity, in which case the denominator becomes infinity times infinity. And so the result is 0. Understand that this becomes infinity times infinity, okay? That's what's happening with the denominator. All right, in this case, if we plug in, we get 1 to the power of infinity, because sine is 0, cotangent goes to positive infinity. I hope you remember the graph looks almost like this, right? Almost like y equals negative x cubed, starting with x equals 0. So we can use L'Hopital's rule in the following manner. If we call this expression y, now we take a natural log. Anytime you have a function being raised to the power of function, one easy way to take care of it is take the natural log of both sides. If we take the natural log of both sides, then cotangent x sits in front, and it becomes a coefficient. Now, cotangent x, if we take it down, division by tan x. Remember, cotangent x is 1 over tan x. And now if you plug in, replace the x with 0, and you get 0 over 0, which means we can use L'Hopital's rule. By the way, remember we are using the natural log here.
Ugh.
0/0. And now we can use L'Hopital's rule. Taking the derivative of the top, you flip this over, you get 1/1 plus sine 4x, and then times the derivative of the argument of log, which makes it 4 cosine 4x. So sine becomes cosine 4x and times 4. And over the derivative of denominator tan x, which gives us secant squared. Now, if you plug in, you replace the x with 0. I hope you realize this is cosine of 0, which is 1. This makes it 4. This is sine 0, which is 0. So this makes it 1. So 4/1. And secant is 1/cosine. Remember that. So this is 1/1 squared. This is 1. This is 1. This is 4. And therefore, our answer is e to the power of 4. Anytime you take a natural log, a short way is just to, whenever you get to the final answer, your answer for the question would be e to that power that you found. Asymptotes. I hope you remember when we are dealing with rational functions. In order to find various asymptotes, the vertical asymptote, you set the denominator equal to 0. Horizontal asymptote, you take a limit and you let x go to infinity, or one easy way, you look at the degree of the numerator versus the degree of the denominator. When the degree of the numerator and denominator are the same, the leading coefficients take over. If it's less than the denominator, then y equals 0. And if it's larger by precisely 1, we have a oblique asymptote that can be found by taking the long division or synthetic division. So let me just quickly write this for you. So VA, basically the denominator is 0. That is one easy way to do it. Now, if we happen to have a sub n x to the power of n all the way over a b sub m x to the power of m, then horizontal asymptote, if n is less than m, it's y equals 0. If n equals m, y is equal the coefficients, as I said, a sub n over b sub m, the leading coefficients. And if n oblique asymptote, if n is equal to m plus 1. Oblique or slant. Okay, so that's the general idea. Okay, so let's say vertical asymptote x equals 1, horizontal asymptote doesn't exist simply because the degree difference is more than 1. There's a degree difference. The numerator has a higher degree, doesn't matter by how much. So that's how that works. Now, we can do the long division or synthetic division, and we rewrite the expression f of x as follows. So I'm assuming nobody has any problem with division class. Now, this portion, y equals this portion, the quotient is slant asymptote or oblique asymptote, SA or OA. A quick example of that, if you were to graph this, generally speaking, you can use the rules that you've learned in the previous course, college algebra pre-calculus. We will add a calculus to it, but remember, when you're dealing with a function like this, that can be a little bit more involved. So finding the intercepts is very simple. X is 0, find y is 0, find x. So if y is 0, a fractional expression is 0 when the top is 0. Okay, so x minus 1 equal to 0, x becomes 1. That's how you find that. And that's the point. Y-intercept, set x equal. If you set x equal to 0, these two are 0, so you get negative 1 over 1, which is negative 1. So we got those. Asymptotes, vertical asymptote, denominator equal to 0, so x equals negative 1/2. Degree of the numerator and denominator are identical. Horizontal asymptote, 1, y equals 1/2. By the way, it's important to, so x equals negative 1/2, that's the line, and it is a dashed line. Y equals 1/2, and I hope again you realize the coefficient for x is 1 here, okay, class, 1 over 2. And there's no slant asymptote because you have either or, not both. All right, as far as the pre-calculus is concerned, the easy way to graph this, remember, there are two pieces here, one on the, there, because you have one vertical asymptote, there's one piece on the left, one piece on the right. On the left, either goes like that or like this. And because we do have these two, pretty much we go like that and not like that. Not only that, in order for it to go this way, you need another y-intercept. On the other side of your vertical asymptote, it goes like this or like that. And the reason this is not acceptable because that means I need one more x-intercept. So pretty much I already know the graph looks like this, okay? Because all you need, pick up a point on each side. Again, this side we have 2, on this side we can pick 1. To the left of the vertical asymptote, remember the vertical asymptote x equals negative 1/2, for example, pick negative 1, plug in and calculate, okay? So we're done with that, but to add derivatives and domains and so forth, let's differentiate. I'm assuming everybody can differentiate this using the quotient rule. Okay, the top gives you 1 times 2x plus 1 minus the bottom gives you 2 times the top over the bottom square. This is f prime g minus g prime f over g squared. By the way, the domain is all real numbers except what makes the denominator 0. We already have the vertical asymptote, so everything except that. By the way, the methodology we write that, normally we write it in an interval notation in the following manner. Okay, and here's the f prime of x. We simplify, we get this one. And I hope you realize that even if you don't do the sign graph, this is always positive. How do you know that? Because you have an expression where the numerator is a number. It's a positive number. And the bottom is being raised to the power of 2. That means it is always positive with the exception of what makes the denominator 0, namely x equals negative 1/2. So if you were to do the sign graph, it will look like this. So it's important to understand that because it's increasing here, we don't have any extrema because the extrema happens when there is a change. So no extrema. The way we write this from negative infinity to negative 1/2 union negative 1/2 to infinity, basically what I wrote here, okay? It's increasing everywhere, but you can't say from negative to positive infinity because there is a break. We do f double prime. One easy way, write this as 3 times 2x plus 1 to the power of negative 2 and differentiate it plus. Okay, so write this as 3. Let me write that. You can write this as 3 times 2x plus 1 to the power of negative 2. Anytime the numerator is just a number, you really don't have to do the quotient rule. This is the fastest way. So 3 times negative 2, 2x plus 1 to the power of negative 3 times 2, and it becomes negative 12 over 2x plus 1 cubed. And we can do the graph as follows. You pick up a test point, any number to the right or left, and you pick it up. If you probably go to the right, the easiest choice would be 0. If you plug in 0, this becomes positive. Negative 12 over that is negative. And to the left of negative 1/2 times negative 1, or you may notice because this is an odd exponent, they will alternate, meaning that over here it's concave up, over here it's concave down. However, so concave up, positive, concave down. However, we don't have an inflection point because x equals negative 1/2 is not part of the domain. If it were, we would put it in there and find the pair. So the other thing that is important, we found the horizontal asymptote to be equal to 1/2. You have to set f of x. You have to set this equal to horizontal asymptote. If there is any solution, that means this crosses the horizontal asymptote at that point. You have to check it. This is an empty set. There is no solution. So just graph the function and you're done. So I hope you see why, using the methodology, it does take a little bit of time to get to the answer. So a quick recap. Use the old stuff, finding the intercepts, the domain, asymptotes from pre-calculus. Pretty much you have the graph. All you need is a pair on each side, sometimes more than a pair on each side of your vertical asymptote or vertical asymptotes. But we can add information from calculus to find the increasing, decreasing interval, if it's concave up, if it's concave down, so on and so forth. The idea of optimization, there are some examples for optimization. We want to find two numbers whose sum is 54 and whose product is a max. A farmer wants to fence a rectangular field besides a river with 2,400 feet of fencing. The river itself will be on one side. What dimensions will maximize the area? A box with a square box and open top must have a volume of 5,324 cubic centimeters, so on and so forth. These are some examples of optimization. Needless to say, we don't have time to do all of this, but those are some examples you come across. So in this page, if we look at one of them, let's say number 2, it starts with a setting. I can't emphasize the importance of the setting. Do the drawing, and this is x, this is y, and your objective function becomes maximize the area, which is x times y, with the constraint, which is the perimeter, normally 2x plus 2y, but because one side doesn't need fencing, would be 2x plus y only, equals 2,400. This is the translation of your question. You want to maximize the area. There are two variables. We solve for one of them and we put it in. A becomes a function of one variable as follows. So y is 2,400 minus 2x. Replace it, and a couple of things that are important to notice. Number one is you are going from two variables to one variable. Number two, what is our domain? X represents sides, has to be positive. Well, why is it between 0 and 1,200? If you set the second piece, which is a parenthesis equal to 0, x becomes 1,200. If you pick a number larger than 1,200, this parenthesis becomes negative. The area becomes negative. Therefore, this is the open interval, and I write it in this format also, of 0 to 1200. That is extremely important, and I'll tell you in a moment why. So let's find the critical point. A prime 2400 minus 4x, set it equal to 0, becomes 600. Now, when you come this far, you just found the critical point. Now you find a double prime, and you really have to plug in 600 because it's a constant. You don't have to. Negative means concave down. Negative means concave down, looking like this, the maximum. Now, the first or the second derivative test, in this case, we use the second derivative test, can tell us if we have a local max or mean, not absolute. So local max at this point. But how do we know this is absolute? Because this is an open interval and there's only one critical point. That's why it makes it important. So you use either this one or that one, you find y, those are the dimensions, and that's the area. Very straightforward. A box with a square base and open top must have a volume of 32K cubic centimeters. Find the dimensions. That will minimize the amount of material. Again, this is a rectangular solid. We should know the surface area and the volume. The volume is the base, the area of the base times the height, which is normally length times the width times the height. In this case, becomes x squared times h because the base is a square. The surface area, we have 4 walls. This case happened to be x times h times 4 of them. We have the base, which is x squared, and the top x squared, 2x squared. However, open top only 1x squared. So objective, minimize the surface area, 4xh plus 2x squared, with the constraint being x squared h. The volume is 32,000. We solve for h. We put it in the surface area because that's what we want to minimize. That's the objective function, and it has 2 variables, h and x. We're going to get rid of the h. We rewrite this as follows. Pay attention to this one. This becomes 128,000 x to the power minus 1 plus x squared. You can put the x at the bottom, take a common denominator, you get this one. Yx is positive because it represents dimensions, sides. This one makes it easier to differentiate. So we got the function s prime of x. The reason we differentiate because we are looking for critical point or points. So this will result in negative 128,000 x to the power minus 2, and this results in 2x. Now, from here to here is a basic algebra because x squared is the denominator. You take a common denominator, and this is what you get. The reason we go this route because of the next step. The next step being, how do you find the critical point or points? S prime equals 0, S prime doesn't exist. When S prime is 0, the top is 0. We're going to solve that. When S prime doesn't exist, the bottom is 0, which makes x equals 0, not part of a domain. So I can write the domain 0 to infinity, which is an open interval. So x equals 0, it's not there, forget it. Let's put the numerator equal to 0 and solve for x, which results in 40. This is a critical point. Is this going to maximize or minimize? We have a choice of going with the first or the second derivative test. The second derivative test is easier. S double prime, here's S prime. We get S double prime. Negative times negative makes it positive. And I hope you realize it means 256,000 divided by x cubed plus 2. Now you have to plug in 40. This is 256,000 over 40 cubed. You don't even have to evaluate it to know this is positive. Plus 2 makes it positive. Positive means concave down, concave up. This means concave up. And minimum occurs at the critical point, and therefore this is an absolute mean because we have an open interval and there's only one critical point. You plug in and you find all the dimensions. You can also find the surface area. They were asking for the dimensions, but we could also find the surface area if we are asked. Something slightly different. What is the minimum distance between the two parabolas? The very first thing is to graph it. I hope you know how to graph this. This is y equals x squared shifted up by 1. This one, you see that it opens down. X equals minus b over 2a is the location of a vertex, a couple of pairs, meaning intercepts, and you have the graph. Therefore, the moment you see the graph, you see the minimum distance would be a minimum vertical distance. If we don't know where it happens, the x coordinate, we call it x. For the top one is the y coordinate is x squared plus 1. For the bottom one is x minus x squared. So we are minimizing the vertical distance. Now, of course, this is using the distance formula. And we can look at the square of that. It doesn't make any difference. I hope you really remember the distance formula. The distance formula is the square root of x sub 2 minus x sub 1 quantity squared plus y sub 2 minus y sub 1 quantity squared. You take a root. Now, if you square both sides, that works the same way. As you look at the x coordinates, x minus, so x sub 2 minus x sub 1 becomes x minus x, they cancel each other. And the second part, y sub 2 minus y sub 1 is the top minus the bottom, right? And we are taking it outside the square root. It makes it easier. Simplification will give us this. We don't know where this is going to happen. Can happen anywhere. There is no restriction on x. So x goes from negative to positive infinity, which is an open interval. Let's do optimization by taking the derivative. Set it equal to 0 and x becomes 1/4. Now we can go with v double prime, which is 4 positive concave up, means minimum occurs at this point. And because this is an open interval and there is one critical point, it is not only a local, it's also absolute. So minimum occurs when x equals 1/4. Absolute minimum is to evaluate this. And we have the answer. So what is the minimum distance between the two? We have it. Another example, a cylinder is inscribed in a cone with a height h and base radius r. Find the largest possible volume of such a cylinder. So drawing a setting is extremely important. We have a cone. We have a cylindrical shape. This is the height. If this is the lowercase h representing the height of a cone, lowercase r representing the radius of a cone, and capital R represents the radius of the cylindrical shape, and capital H representing the height of that. Remember, in each case, for example, the volume for a cylindrical shape is the area of the base pi r squared times h. So the volume is pi r squared times h, where the radius is represented by x and the capital H, if we call this distance y, everybody. If this is y, then h is lowercase h minus y. The reason we do that, because h and r is fixed, lowercase h and r. Let's write the formula as pi, r squared becomes x squared, capital H becomes h minus y, and the volume is a function of x and y, x and y. So we have two variables, namely x and y. Let's go with a similar figures. If we look at this, maybe I do the drawing. And we are looking at just a triangular shape here. So from here to here is x, from here to here is y, this whole thing is h, this whole thing is r. We have two variables, x and y, and we want to go to one variable, so we can use a similar figure. So we can see the relationship, for example, in the smaller one, y to x is the same as h to r. And therefore, we can solve for one of these variables, either y or x, and replace it here. In this case, we're going to solve for y and replace it here. So I hope you see that the hardest part is actually the geometry and trigonometry involved. So we do that. So we are trying to write this as a function of one of those variables, x or y. So pi x squared, h minus, and we replace the y. And why is it that x is between 0 and r? I hope you realize this is x, this is r. X, can it be 0? No, because if it's 0, we don't have a cylindrical shape. Can it be r? No, because if we do, then we don't have a cone. So it's somewhere between, in between. We take the derivative. Now that it is a function of one variable and we have our domain, we are ready to move on with the calculus part. Everything done is so far pre-calculus. V prime, okay, x squared becomes 2x, you put the 2 in front, minus pi h over r is just the number, is the coefficient, times 3x squared. So that's the derivative, and we can factor out the pi hx. This gives us 2, and this gives us minus 3x over r, which means if we set v prime equal to 0, either x becomes 0 or this parenthesis becomes 0. X is 0. If you set the parenthesis equal to 0, 2/3 r. We go back to this. Can it be 0? No. Is this number between the two? Yes. So this is the only acceptable critical point. So the maximum occurs at x equals 2/3 r, and you show that by doing the first or the second derivative test. So you really have to go with v double prime. Okay, so it's easier to go from here. I leave it for you to find v double prime and plug in 2/3 r and show this is negative, and that is the proof. So this is for you to do that. As far as the volume is concerned, we can replace the x with 2/3 r to find the volume. which is 4/27 pi r squared. So again, find v double prime evaluated at 2/3 r. Show that it's negative. Find v of x, which is purely algebraic. We want to look at the Newton's method quickly. The Newton's method says if you're interested in finding the next value for x sub n, if you are looking to find zeros of a function, roots of a function, you can go with this concept. And this is from the fact that the x-intercept of a tangent line is very close to the x-intercept of a function. So in essence, you're really finding the tangent line and you manipulate that. That's what Newton's did, okay? So x sub n plus 1 is x sub n minus f of x sub n over f prime of x sub n. So what I want to add is this. You have to show work, and you'll see it as we look at a couple of examples quickly, up to a certain degree, and then it becomes involved, really involved. You can use a calculator. I have shown it in my PowerPoints, and I'm repeating it here. You can use a calculator for that part and that part only. And you can even use the cylinder program. You let y sub 1 represent f of x, y sub 2 f prime of x. And wherever you begin, let's say x equals 2, 5, 7. Store it in x, and you plug this one into x, enter, it gives you all the values. What do I mean by that? I make it clear with a simple example in a moment. Now, what I'd like you to see is this concept again that was discussed in the PowerPoints, and that is you are given a function and you're looking for its roots. So you pick a point and you draw a tangent line. Now, when you draw a tangent line, the tangent line will cross the x-axis at some point. If it doesn't, then that one fails, by the way. So now, this belongs to the tangent line. So you come up with the equation of a tangent line. Everybody knows how to come up with the equation of a tangent line. You need a pair. You picked up a pair. You need the slope. Find f prime of x and plug in the pair. So you have that. Now, what is the x-intercept? You set y equal to 0. That's how we arrive at this equation. And you keep on doing this until you get to a point which is the actual root of the function. So as an example, we want to approximate this to 8 decimals. And I've given you the formula here for the program that you can use for your calculator. So if we want the 8th root of 500, how do we get this started? First, you have to write down, this is what you're looking for. So this is your x. Therefore, x to the power of 8 is 500. So you have to write this. The next thing you have to write, okay, what is my f of x? You can bring it to one side, and it doesn't matter which side, call it f of x. So you need to come up with f of x. You also need to come up with f prime of x. Okay. Now we want to show this. We want to show this for one point using this formula. So if we use this formula with the fact that f of x is this and f prime is this, the numerator is f of x sub n. So is this one. And now let's do one. You can do, and you should do one with hand. Where do you begin with? If they give you the first point, so be it. If not, you have to do it on your own. Notice that 2 to the power of 8 is 256, 3 to the power of 8 is 6,561. You start either with somewhere in between or even number 2, because we are going to go with the programming. It is doable, so it's not a problem. Having said that, if we choose 2, we plug in here and we get, that's the first one, right? X sub 1. Now x sub 2 would be plugging in. So let us start with number 2. So write this for x sub 2 and x sub 1, and let's plug in. This is what I mean. You have to show your work here. And when x sub 1 is 2, this thing with a lot of decimals is this. Obviously, you've shown your reader, you know the steps, and we don't want to waste time. Now we use a calculator. And that's what I'm saying. It really makes your life easy if you follow that, but you have to show up to here. So you're going to store the 2. So if you were to do it by a calculator, you store the 2 in X, 2 store in X, then X minus Y1. So X of 1 into X, we're in the third step, okay? And we have written those in the first 2 parts. X minus Y1 over Y2, store it in X of 2. And all you have to do, repeatedly press enter, enter. Because it says 8 decimals, take a look, 1, 2, 3, 4, 5, see they are different. So that means right away you realize you're not done. So you do it again, and now you find the fact that you want with 8 decimals. So you go with 1, 2, 3, 4, 5, 6, 7. This is 8, and you can change that because of this. And they agree. You don't have to continue anymore. A quick example of another example of Newton's method is as follows. You want to use Newton's method to approximate the positive root of 3 sine x equals x to 6 decimals. And again, for a case like this, you could guesstimate, but they want you to start with the graph to have an idea what we want. There are 2 points, but we want the positive root. Okay, so these are the roots of intersections, by the way. So if you graph this as follows, y equals 3 sine x and y equals x, the points of intersection. So we write this as to a function bringing 1 to the other side. It doesn't matter which one. And if you bring x to this side and you call it f of x, you find f prime of x easily. And you write the formula for Newton's method. So so you need the function, you need f prime, you need the formula, and using x of 2 equals x of 1 minus 3 sine x of 1 minus x of 1 over 3 cosine x1 minus 1. We use 2 because I hope you see 2 is close to this. And now you use a calculator. So if you use x of 1 equals to 2 and plug it into a calculator, you get to this number. X of 3, you get this number. We are using a calculator at this point. After you write all of this, and by the way, 2 is in radians. Now look at the calculator work. We wanted with 6 decimals. And there you have it. To 7,886, and this 2 changes to 3. Okay, anti-differentiation or integration. There are basic formulas. Hopefully everybody is familiar with. Just reverse the process of differentiation. So we have to be extremely comfortable with differentiation to be able to handle this. As an example, if we want to do this one, here's the process. Sometimes you need to simplify first, factor, cancel, remove radical notation, etc. Sometimes you need to integrate using substitution, which is coming up. But basically that's it. So when you look at this one, this is fine. This guy, we can cut it into 2 fractions. Square root of x is x to the power of 1/2. In other words, first and foremost, do your algebraic techniques to write it such that you are ready to integrate. So you're going to integrate the right side. And since you're integrating, you tag along dx. Remember, the derivative of sine is cosine, but the integral of that is negative. Therefore, minus 4 cosine x plus 2 over 5 x to the power of 5 minus 1 over negative 1/2 plus 1 x to the power of negative 1/2 plus 1 and a constant. This is the power rule. Now, this is, of course, 1/2. 1 over that becomes 2. And there you have it. Again, the reverse process is extremely simple. If you are comfortable with differentiation, this goes extremely fast. All right, again, I do have the rules here for you. The power rule, the integral of x to the power of n dx is 1 over n plus 1 x to the power of n plus 1 plus a constant. This works everywhere with the exception of x to the power of -1 or 1 over x, which becomes a natural law. So we do this step by step. This is 2 over 5x to the power of 5 plus 3 over 4x to the power of 4 minus 7/3 x cubed plus x becomes plus 1/2 x minus 5x and a constant. Easy way, square that. And now this becomes 1/3 x cubed minus 10 over 2. That means minus 5x squared plus 25x and a constant. Even if we are differentiating, our first step for this would be algebraic techniques as follows. 1 gives you x. Pay attention to this because it's dx, it gives you x minus 7 times 1 over x minus 7 times ln x. And then 2 over x squared, you can rewrite it as 2x to the power of -2. So you can use the power rule on that. And only this part gives you 1 over -2 plus 1 x to the power of -2 plus 1. And that results in -2 over x. And of course, you're writing the whole thing. Therefore, the answer is x minus 7 ln x with an absolute value. This becomes -2 over x and a constant. So since this is dt, 1 gives you t, not x. That's something I want to mention that because sometimes students make a mistake. Plus cosine. The derivative of cosine is negative sign, but the integral is positive. And as always, a constant. Cube root of x, you change it to x to the power of 1/3. And that one, you write 1 over 1/3 plus 1, x to the power of 1/3 plus 1. 1/3 plus 1 is 4/3. 1 over that is 3/4. So you write this, and the derivative of sine is cosine. The integral is negative cosine with negative makes it positive. Initial value problem. Basically, we are doing the same thing as before with an added bonus of a pair. So for now, we're going to ignore that, see how that works, and then I'm going to add that. So the definition is any equation containing a derivative is called a differential equation. A function which satisfies the equation is called a solution to the differential equation. An initial value problem is a differential equation along with a specified value of the unknown function called the initial condition. So in this case, I'm going to put the dt on the other side, and I'm going to integrate. You remember when you differentiating, you multiply by 3, but integration, we divide by 3. And we would be done if we didn't have this pair in essence. This means we have the pair 0, 1. So this is a general solution. General solution. Now, we replace the t with 0 and p of t with 1. I hope you realize this is 1. So 2/3 plus some number is 1. That number must be 1/3. And now we have a particular solution. So What is the initial value problem? It's just a good old integration problem with the added pair going from a general, because a constant means we have infinitely many solutions. We have a family of functions now, the C is known. It's an initial value problem. So one particular solution. A particle moves in a straight line, we call it a rectilinear motion, and has acceleration given by a of t equals 60 plus 4. Its initial velocity v of 0 is negative 6 centimeters per second. Initial displacement is s of 0 equals 9. Find the position function. In other words, you want to integrate this. That's the idea. So what is given is the derivative of the v. So a of t, remember, s of t differentiated gives you v of t differentiated gives you a of t. So v of t, the reverse process, very fast, 3t squared plus 4t plus c. Write this pair and use that. In other words, replace, we are using this, replace the t with 0, and v of t becomes negative 6. I'm assuming everybody can see 0 makes everything 0, so c is negative 6. And that's the function v of t. What about s of t? We integrate again. So this gives you t cubed, 2t squared minus 6t plus t. And s of 0 is 9. So replace the t with 0, everything becomes 0, plus d equals 9, d becomes 9, and you're done. One more quick question here. If we are doing this, we first do the algebraic technique to cut this into two fractions. This gives you x. This one we have done it. You can look at the previous page. And secant squared, remember, the derivative of tangent is secant squared. So that's why we have it tan x. Continuation with the integration. In the next chapter, we are given differentiation formulas. Logs. Many logarithmic properties. Integration formulas that were discussed before. Now, in this chapter, we start with the area and distance. Suppose a continuous function f is defined on the interval of a to b. If the interval is divided into n subinterval, it gives rise to what we call a Riemann sum. So the summation of f of x by delta x as I goes from 1 to n is f of x of 1 times delta x all the way to the last one, where delta x is b minus a over n. We are cutting the interval into n subintervals. So partition the interval into, for example, 4 ways. It makes 4 rectangles. If you do it, eight rectangles, okay, however many. We have the left endpoint rule, left endpoints, right endpoints, and midpoint. Instead of memorizing this, I'm going to show you an easy way to do this with a simple line segment. What this really refers to, when you have a rectangular piece, the width is fixed at delta x, which is calculated as b minus a over n. But what is the height? If you're using the left endpoints, the very first point counts, so f of x of 0, all the way to the last one, but not the last endpoint. In the case of a right endpoint, the very first one, which was f of x of 0, doesn't count, but you go from the next one all the way to the last. And the midpoint, you use the middle of the 2 points, x of 0 and x of 1, and you evaluate the functionality. Again, what does it mean? Let's look at an example to make it easier. Now, Area under a function f of x when it's a continuous and a positive function is approximated by this Riemann sum. If you take a limit and let n go to infinity, it becomes the actual area. Now, here's what I meant by using the right endpoints and left endpoints. We want to find this, and as you know, with the fundamental theorem of calculus, this can be done very fast, but we want to use left endpoints, right endpoints, and midpoints as follows. So you have the graph. If we want to go from 1 to 2, so you want to go from here to here. So you want this area, which is hard to show. It's small, but somewhere from here. This is what we want. So we want to approximate this using the left endpoints or the right endpoints. So from 1 to 2, I'm going to draw a line segment. Take a look. This is 1. This is 2. I'm going to cut it into how many pieces? N pieces. N happen to be 5. So delta x, the function f of x is 1 over x. A is 1, b is 2, and delta x is b minus a over n, which makes it 0.2. So we have this. Now we have this from here. So first write the function. Here's a, here's b, a, b, here's delta x. And why am I writing this? Because now it helps me with all those left and right and midpoints, and here's the easy way. Now, if you look at the left endpoints is delta x, we have the delta x times f of x of 0. So f of what? Look at the left endpoints. You have, if you look at the dots, you have 1 tick marks, 1, 2, 3, 4, 5, 6. For the left endpoints, use all of them except the last one, b. The function is 1 over x. So 1 over 1, 1 over 1.2, 1 over 1.4, all the way to 1.8, and you write it with a bunch of decimals. If they don't give you, you put many, 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 many decimals. For the right endpoints, again, go back to this line segment. Use all of those except the first one. Take a look. So we start with 1 over 1.2. By the way, notice when you do the calculation, these two are identical. Therefore, you want to keep that as you go from the left endpoints to the right endpoints. You don't have to do a lot of calculations. I can't, emphasize this enough. If you have the left endpoints and if you kept that, this goes extremely fast. And again, with a bunch of decimals. And finally, for the midpoint, you just locate the midpoint here. As an example, the first midpoint class. Here is 1.1. So what is the next one? Add 0.2. And go all the way to the end. So notice what's the midpoint. F of 1.1, F of 1.3, all the way to F of 1.9, which means this. I just wanted to show you that. By the way, the midpoint is the best approximation. Other approximations, depending on the shape of a graph, they overestimate or they underestimate. And there are other methods of doing that. The best one is, at least among these three, is always the midpoint. But I hope you appreciate the importance of this line segment and how fast you can come up with the answer if you use this line segment. So that's the answer between the two numbers, because one overestimates and one underestimate. And how do you know that? If this was large enough, you could see the rectangles clearly. They are underestimating or overestimating. The definite integral, basically the Riemann sum that we were discussing. The area under the curve becomes the limit of that Riemann sum, and it is defined as this. So the integral of a to b f of x dx, which is called the definite integral, by definition is equal to that. The limit of f of x, summation of f of x of I delta x, as I goes from 1 to n, as n goes to infinity. So this is by definition, where delta x, by now we know it's b minus a over n, and x sub I is a plus I delta x. This is one way to do it. This is using the right thing, the right endpoints. So let y be f of x, a continuous and non-negative over an interval, a definite integral as n goes to infinity of the Riemann sum of the area of a rectangle under the graph of y equals f of x, where ab is given as such. Please understand we are looking at this one is a definite integral and is defined by that, and it becomes the area under the curve under the following conditions. A continuous function and non-negative. If it happened to be negative and positive, then we are looking at the difference of areas, the net area. That's a slightly different story we discussed. We want to express this as an integral, which means write this. This is the definite integral, everybody. The integral of a to b lower limit, upper limit f of x dx. And this is the Riemann sum, the limit as n goes to infinity of summation of f of x sub I delta x. Because it's the limit, that means you're given this, and we want to find this. So 0 to 2 pi, a and b are 0 to 2 pi. So let's compare this using this formula again. So we have the right side in essence, okay? So the right side is as follows. We want to see from a to b. So a is 0, b is 2 pi. Remember, delta x is b minus a over n, and x is a plus I delta x. Let's figure it out. So delta x is b minus a, 2 pi minus 0. 2 pi minus 0 is 2 pi over n. And x sub I is a, 0 plus I times delta x, so 2 pi I n. And as you can see from here, pretty much a is 0, b is 2 pi, obviously. And f of x becomes sine x in the interval of 0 to 2 pi. This is just by inspection. There's really not much to it, class. You have to inspect. And therefore, this becomes the definite integral of a to b, 0 to 2 pi, sine x dx. Sine x dx. In other words, this changes to x. This is delta x changes to delta x changes to dx, and this is the sine of x. If you recall, when we did the differentiation, there was a case where we did it by definition. When we do definite integral, normally we don't have to do it by definition, but there will be a question with the definition. We want to know how it's done by definition, although it's a lot easier to use FTC, fundamental theorem of calculus, okay? So let's go with the definition for this question. With the following facts: the summation of 1 is n, the summation of c is nc, the summation of I is n times n plus 1 over 2, so on and so forth. So how do we do that? First, we notice this is the case. Delta x is b minus a over n, x of I is a plus I delta x. And we notice that a is 0, b is 2, and f of x is 1 minus x squared. So with that being the case, we can see that delta x is b minus a or 2 over n, and a plus I delta x, a is 0 plus 2I over n. So I hope you see that from here, because a is 0, b is 2, and right here, delta x b minus a, b minus a, 2 minus 0 over n. So having said that, let's plug in f of x sub I. Remember, f of x is 1 minus x squared. So let's plug in x sub I. So 1 minus 2I over n quantity squared in the parentheses or brackets times delta x, which is 2 over n. So f of x sub I is this. Delta x is this. Let's distribute 2 over n times 1 and times this one. This one, by the way, is 4I squared over n squared. And so that's what we have. When you want to evaluate this, remember, we are interested in finding the limits. So we are writing this without the limits. We have to evaluate the limits. So we are simplifying this. We want to simplify such that some of this stuff show up. So I can see that the summation pertains to I, so I remains and everything else comes out. So this one I can say 2 over n times the summation of 1, and this one I can get 8 over n cubed times the summation of I squared. I hope everybody can see what I'm doing here. The summation pertains to I, so I, anything involving I remains. So what about summation of 1? I can replace it with n. What about summation of I squared? I can replace it with n times n plus 1 times 2n plus 1 over 6. Let's do that. So what matters here, because remember, we are going to take a limit later on. First, this simplifies to 2. It's not a problem. The second part, what I want you to notice is this. This part, if you were to multiply, you get 2n cubed as the very first term. And I'm not going to even write the rest because we know the rest are going to have a smaller exponent. Therefore, we have the following. Notice what I have written here. I want to make sure everybody understands. So this is 2. This is minus 8 times 2 minus 16n cubed. The rest are not important. Why not? Because we are going to take a limit as n goes to infinity. And when we take a limit, see now I'm putting the limit. This is 2. And I hope you remember when you have to divide by the highest degree term in the denominator, which is n cubed, when they have the same degree, it's just the coefficients that take over. So 2 minus 16 over 6, which gives us the following answer. It's a very straightforward process. Now we're going to use the signed areas, the net theorem, if you will, to come up with the answer. First, notice the function of interest. This is using the areas. The function of interest, y or f of x is x, and we are evaluating it from -1 to 2. And that is a simple graph. Y equals x, remember the line that goes through the origin. Using the signed areas, we're going to go from -1 to +2. This is positive. You calculate the area as 1/2 base times the 8, 1/2 base times the height. In this case, this is located at 2 and 2. That means the base is 2, the height is 2. So 1/2, 2 times 2. This one located at negative 1, 1. That means the height and the base are both 1. That means 1/2, 1 times 1. So we are using this formula. This one is 1/2, 2 times 2. This one is 1/2, 1 times 1. We're going to subtract the red area from the green area. We want to use geometry to evaluate. We can't do this in using calculus 1. We'll discuss that in calculus 2. So it has to be done using geometry. Any other way is unacceptable for this course. So you notice this is a semicircle because if you write this as y and square it, y equals this and square it, you get y squared. Let me write that. If you square it, you get y squared is 9 minus x squared. You bring it to the same side, you get x squared plus y squared equals 9. If you recall, x squared plus y squared equals r squared is a circle centered at 0, 0 with the radius r. Therefore, we have a circle centered at 0, 0 with the radius 3. So we know how to calculate the area, which is pi r squared, and we want half of that. Again, a circle, the area is pi r squared. The reason we want half of it because it's a semicircle. So the graph is extremely important to show the process, and also algebraic step to show that you are dealing. You must prove you have a circle, and in this case, a semicircle. Okay, so this is a circle, this is a semicircle. Given the integral of 1 to 3 f of x dx is 6, 3 to 7 is 9, 1 to 3 g of x dx is minus 4. We want to find the following. So 1 to 3, 3 times. So for this one, we have it, just take the 3 out, do the math. We do the same thing. We take the 2 out for f of x, 4 out for minus 4 out for g of x. So we have this one, plug it in. We want 1 to 7. We know 1 to 3, we know 3 to 7, and so we can write it as 1 to 3, 3 to 7, as long as the lower limit of the first and the upper limit of the last are the same, then it's from 1 to 7. Finally, if 1 to 3 is this number, then 3 to 1 is the, you negate that, is the opposite of that. That's the idea to remember. We come to FTC. In FTC, there are two cases. One is that if you want to evaluate the integral of f of x dx from a to b, find any antiderivative and evaluate it at the limits, okay? And this is the faster way. If you remember, we just did this by definition of a Riemann sum. So this is a fast and easy way. And this one says the derivative of the integral is the function itself. What you need to see, this variable, which is called a dummy variable, these two must be the same. And then x is replacing that. Derivative of that is that. It's extremely important to pay attention to that. We want to evaluate this integral. From -2 to 2. By the way, I wrote, even if it were from -infinity to 0, 0 to infinity, it would actually work the same way, conceptually. So with that being the case, this function is cut into two pieces, from -2 to 0, and then from 0 to 2. From -2 to 0, we use the top function. This is a piecewise defined function. And for 0 to 2, we use the bottom function. And that's really the key. How do you integrate a piecewise defined function? That's the key. So this gives us 2x from -2 to 0. This gives us 4x minus 1/3 x cubed from 0 to 2. This becomes now algebra. You plug in the top, you plug in the bottom. So I'm going to show you. This is the part you can't afford to make a mistake. This is algebra class. Plug in 0, evaluate it. Plug in -2, evaluate it, the difference. Plug in 2, evaluate it. Minus, plug in 0, evaluate it. Put them all together. I'm assuming everybody is okay with this. Everybody can easily come up with the answer. This is a simple case. So from here to here is calculus. Everything else is algebra. Find the derivative of the function. And this is a fundamental theorem of calculus, reminding you d dx of a to x f of t dt is f of x. So basically, they want the derivative of the integral. That means the function itself. And you basically replace the variable here, whatever it is, with this upper variable. This is a continuous function. I hope you realize why, because this is a square root of 1 plus t squared. The domain is all real numbers because 1 plus t squared is always positive. It has to be larger than or equal to 0. And this is a root function. It's a continuous function. Therefore, we use FTC. And we replace the t with this upper limit, and we are done. Pay attention to the fact. The lower limit is a number. By the way, does it have to be 0? Any number will do it. Any number will do it. The upper limit will take over as the new variable, if you will. Now, take a look at this one. We've gone over the proof of that. If you're taking the derivative and now the upper limit over here is x, but over here is a function of x, then remember t was replaced by x. So the same thing is going to happen. T will be replaced by this upper limit g of x. However, by the chain rule, we multiply by the derivative, which is g prime of x. So therefore, we're going to replace the t with x squared, and then times the derivative of x squared, which is 2x, and we put that in front. So I want to make sure everybody understands what happens one more time. The upper limit will take over for t. The upper limit is x, we are done. If it's not, by the chain rule, times the derivative of that, which is times 2x, and we put it in front. Another way to do that, you can actually do this, ignore d dx. If you integrate sine, you get negative cosine. Evaluate it from 1 to x squared, and now take a derivative. So I highly recommend you do this. Ignore the d dx, integrate this one, and you get minus cosine t from 1 to x squared. Evaluate this part, and then take the derivative. It gives you absolutely the same answer. Now with that, if the top is a function, replace the t with that function, and then times the derivative of that. So we're going to replace the t with the top function, and then times the derivative of that, which is 2x plus 1, we put it in front. Now, what happens when the top as well as the bottom is both are functions? We went over the proof of that. If we have a case like that, we plug in the upper limit and then times its derivative. We plug in the lower limit and times its derivative, and a negative sign in between. So I'm going to replace the t with sine. I get sine squared x times the derivative of that, which is cosine, minus, I'm going to replace the t with tan. I get tan squared times the derivative of that, which is secant squared. You can leave it like that. Obviously, this can be simplified, and you can try it by writing it as function of sine and cosine. The secant is 1 over cosine, tangent is sine over cosine, if you want to do that. Either way, it doesn't matter. Now, what happens when the lower limit is a function and the upper limit is not? Just simply put interchange and put a negative sign in front. Notice that sine x and 1 are interchanged and it creates a negative sign. Everything else becomes the same thing. So replace the t with sine x, multiplied by the derivative of sine x, which is cosine x. Keep this negative sign. Don't forget to keep this negative sign. Indefinite integrals and the net change theorem basically tells us that if we are dealing with an application, we can also use this definite integral that has been discussed. The integral of f of x dx from a to b is capital F of b minus f of a. This principle can be applied to all the rates of change in the natural and social sciences. Natural and social sciences. So here's an example. When a fish grow in a way that is described by the von Bertalanffy growth equation for a fish that starts with a length of 1 centimeter and has a maximum length of 30. This equation predicts the growth rate is this 29 e to the power minus x centimeters per year, where x is the age of the fish. How long will it be after 4 years? There are a couple of ways to approach this. Number one, the amount of growth is this. So if the function L of x represents the amount of growth, this is the rate of growth. So L of x or and this one is dx or L prime of x. So that's the first thing. L of x represents the amount of growth. This is the growth rate, the derivative of that. So what is the amount of increase? Therefore, it follows this from A to B, in this case, for the first 4 years, from 0 to 4. Now, this is a simple case. You divide by -1, becomes -29. Evaluated from 0 to 4, you plug in 4, you plug in 0. I'm assuming everybody can do that. And you write it with a bunch of decimals. To begin with, the length was 1, so we need to add 1. And then it's asking for 1 decimal, so we make it 1 decimal. This is one way to do that. I want to quickly share with you the second method. Instead of doing that, we can find the length of a fish, L of x function. Since we have this, L of x will be this plus a constant with the initial value L of 0 equals 1. So take a look. We can say here's L of x. We've already done the work here. So the answer is this plus a constant with this initial condition. If you replace the x with 0, you get 1. So if you do that, 1 equals -29 plus c. So if we plug this in, that gives you 1 equals -29 plus c. C becomes 30. Now, what do we want? We go back to the question. After how long? 4 years. Plug in x equals 4. What is the advantage of that? Which is, by the way, the same as this one. And then you have to pay attention to the number of decimals. What is the advantage of this? If the question had several parts, so what is the length of the fish after 4 years, 5 years, 10 years, 12 years? You don't have to redo this. Just in this equation, replace the x with the number. And that makes it, I think, faster and easier. We want to find the area between the x-axis and the curve, y equals cosine x from 2. That means we want this area and we want this area. If we integrate from 0 to 3 pi over 2, we get the integral, which is the net area, difference of areas. But we are interested in the area, and notice we have to go with the absolute value. This part is positive, so you can keep it as cosine, but this one is negative because it's below the x-axis when you go with the integration. So that's why you take it to negative cosine. I hope everybody understands what's happening here. I can't emphasize this enough. We need to understand that we want the area, therefore it's the absolute value. Now, this one is simple. You can integrate a cosine. The derivative is negative sign, but the integral is positive. This negative creates a negative from 0 to power 2, from power 2 to 3 power 2. And I hope everybody remembers the basic in trigonometry and trigonometric functions. You plug in, you evaluate, and you end up with number 3. What I'd like you to do later on your own, and so distinguish between the two, try integrating this one without the absolute value, which again gives you the net area, the difference of areas, okay? So find this and compare it to what the question is asking and why we are using the absolute value. In this example, we want to evaluate the integral, and we should use a trigonometric identity for sine, which is, in this case, sine 2x is 2 sine x cosine x. Therefore, we can drop the sine x, and that we know the answer is 2 sine x plus a constant. And that's really the key here, being very careful with that concept. Remember, this is 1 over x dx. Therefore, it's a natural log. The reason I'm not using an absolute value, because the limits are both positive. Otherwise, you must. So you really have to write this. But it makes no difference when both limits are positive. It does make a difference if any of them is negative. And so you want to be careful with that. So if both of them are negative, by the way, we can't have one positive, one negative, because if the denominator is x, x can't be 0, so it can't go through 0. You plug in, and 6/3 is 2, so natural log of 2. And by the way, as a calculus student, ln2 is the answer, is a perfect answer, and it's a precise answer. You leave it as such. A particle moves along a line so that the velocity is given. We want to find the displacement from 1 to 4. Displacement by definition is from A to B, v of t dt. So let's quickly find that. A simple case. So 1/3 t cubed minus 1/2 t squared minus 6t evaluated, and I'm going to assume everybody can do that. However, so the particle has a negative answer. That means the particle moved 4.5 meters to the left. That's the meaning of a displacement. So when you move along, it doesn't matter how much you cover, it just the displacement matters, okay? Because we may go like this. The final answer is, so let me actually draw that. If, for example, we go like, we start from point A, and we go like that. And this is the final destination, let's say. The concept is that this is the displacement from here. That's the idea. Now, to find the distance, we find the absolute value of that. And when we look at the function is negative from 1 to 3 and positive from 3 to 4. We find it in this manner. Now, how do we know that? You have to do the sine graph. T squared minus t minus 6 is equal to what? t minus 3t plus 2. We are going from 1 to 4. So as far as the sine graph is concerned, by the way, so this is t. So it makes it negative at -2, makes it 0, at +3 makes it 0. And remember, because t is given, you really don't have to have negative, but this is for the sake of a sine graph. What we are interested in, it's very important, is just this area, to the left and right of 3, because we're going to go from 1 to 4. So to the right and left of 3, if you pick a number to the left of 3, let's say 2, and evaluate this, so 2 makes it negative, because 2 minus 3 is -1, 2 plus 2 is +4, and to the right of 3, for example, pick 4. I hope you realize test point, we pick like 2 here, and we pick like 4 here, it's positive. This negative results in this. And the rest is very simple. You just do your algebraic techniques to finish the job. I'm assuming everybody can do that. Plug in the numbers, evaluate, and that's about 10.17 meters.